to AP Calculus. We're doing optimization today, and we need to do one key example. Good news. It's a Roman numeral structure. Since you already know the Roman numeral structure for related rates, this is going to be just a little bit of a tweak to the Roman numeral structure to get optimization problems. Optimization is a key word in mathematics. It's in the modern math meta-narrative. We're in contemporary times, but back in the modern era, this is a postmodern era that we're in. But here at Wheaton Academy, there are many of the values of the pre-modern and the modern era that we embrace. The modern math meta-narrative that you wrote on your last test was that mathematicians protect and rescue people from suffering by creating meaningful models of unfamiliar real-world situations. And we use these models to do three things. 1, uncover truth. 2, make predictions. And 3, to make decisions that optimize scarce resources. We're going to be maximizing relative maximum using the first derivative or second derivative test, maximizing quantities we desire, and minimizing, using the first derivative test, minimizing things that we do not desire to be present. So here we go, open top box. Let's talk about the open top box concept. And before you write anything down, look right up here. So because of the camera, for people who are absent, if you need to move to a desk where you can get more of a clear sight line, Cindy, you might want to move to a different desk so you can see what's going on. But just imagine that we have an 8.5 by 11 inch sheet of paper. Again, no need to write this down. We're not going to actually do number 2 right here. We're going to do it later. So we're going to use this whole sheet of paper. Maybe you'll want to just look at the length, width, and height of this open top box a little bit on the bottom. But suppose I tear 1 by 1 inch squares out of the 4 corners of this 8.5 by 11 inch sheet of paper. And then I fold up the sides. And to get an open top box, it used to be that my paper was 11 inches long, but now I've cut 1 by 8.5 by 11. So now instead of 11 inches long, the width is now how long? That's what it's called, the length. Well, I cut out of 8. So now it is 9, but I'm going to write that as 11 minus 2 times 1. And the width used to be 8.5 inches, but now I've cut 1 by 1 inch squares out of both corners. So now, how long is the width?
6.5.
Now and 6.5 is correct, but I'm going to write 8.5 minus 2 times 1. The height is now just 1. On your calculator, if you take 9 times 6.5 by 1, you will get a volume of, what is it? Type it in. Type in 9 times 6.5 times 1. You can probably do it in your head. 9 times 6 is 54. It's got to be 58.5. 58.5 cubic inches. Hey, I wonder if I can do better. I wonder if I can optimize the volume. In this case, there's 2 flavors of optimization, maximization and minimization. Let's see if we can get more volume. Here we go. I'm going to now cut a 2 by 2 inch square out of all 4 corners. And when I cut out a 2 by 2 inch square from all 4 corners, and whoa, that was not supposed to happen. We're back. And fold up the sides, I wonder if I have more volume or less volume. I've taken more out, more paper out. Does that mean I have less volume? Let's find out. Instead of the length being 11, now what's the length?
7.
Yeah, 11. Instead of 7, I'm going to write 11 minus 2 times 2. 8.5 minus 2 times 2. On your calculator, if you take 7 times 8.5 minus 4 is 4.5. Type it in. What's 7 times 4.5 times 2? I'm waiting for you to press buttons. Crystal, you've got a calculator. Type in 7 times 4.5 times 2. Now what's the volume?
63.
63? It looks like the bigger x is, the bigger the square I cut out of all 4 corners, the more volume I get. I wonder if that pattern keeps going. I'm going to cut a 4 by 4 inch square. I'm going to let x equal 4. I'm going to cut a 4 by 4 inch square from all 4 corners. Hopefully I'll get a simply ginormous amount of volume. When I cut a 4 by 4 inch square out and fold up the sides, now I've got an open top box that has 11 minus 2 times 4 for the length, 8.5 minus 2 times 4 for the width, and 4 for the height. What is 3 times 0.5? Let's see, 3 times 4 is 12 times 4. Now it's only 6 cubic inches. If I want to optimize the volume, there's got to be some ideal value of x that will give me a maximum volume. Let's do, for the first time, an optimization problem using Roman numeral optimization. Now, the Roman numerals are mostly the same as Roman numerals for related rates. There are some significant differences, though, so let's launch into this. Roman numeral 1. Here the open top box is made from a 15 by 15 inch. So in Roman numeral 1, it's not as complicated here as it was with related rates, because we won't have to be writing down dx dt, dv dt, all that stuff. It's just going to be the same basic idea of diagrams, which consists of cutting an x by x inch square from all 4 corners of this 15 by 15 inch. Let's indicate that the original the original piece of material, we're trying to optimize our use of scarce resources. The assumption here is that the universe is finite, and we want to optimize our scarce resources. So the length, we'll say that this is the length L, the open top box will have a width W, and the height H. Now, one thing that's not defined that we're going to have to define is the volume of the box. So here's where we use the word let V represent, can't just say volume, be specific, volume of open top box. And that concludes Roman numeral 1. It's just the given information and the variable definitions. Less complicated than related rates because we don't have to write down things like dv dt. Now, Roman numeral 2 will not just be a relationship between variables. This is going to be a function. And you remember from Algebra 1 even that some relationships are functions, others are not functions. We want a function. So in Roman numeral 2, instead of merely specifying a desired relationship, we're going to have the same spirit. It's still going to be the goal. But this time we want to have an output variable and an input variable. Now, the output variable, like f of x or like t of x or t of w, how do we think through this? For the output variable, you might want to make a note to yourself if you want to think through this lesson. The output variable is going to be the quantity to be optimized. Here we want volume that is as large as possible. So we want to optimize volume. If they want to minimize time, then you would put a T out here. If you want to maximize something like, or if you want to minimize cost, you might put a C for cost out here. Whatever you're trying to either maximize or minimize is the variable that's going to be the output of the function. For the input, you pick. You'll get the same answer no matter what. We could pick X or L or W or H. Let's all go in the same direction. We need a goal specified. Otherwise, we might start wandering around getting me go. We need to specify the goal. And so it's essentially a relationship between V and X, but we want to have it solved for V. And we want to specify, do we want to maximize or minimize? So, because that tells us whether we're going to look for a relative maximum in Roman numeral 7's first derivative test. Roman numeral 7 could be the second derivative test. I don't care which one you use, but in Roman numeral 7, you're going to use either first or second derivative test. But we got to know whether we're looking for a relative max or a relative min. So decide that in Roman numeral 2, and we're done with Roman numeral 2. Now, Roman numeral 3. And by the way, I will be putting in red the things that are not required for you to write down. So I've got to change this to non-red. Anything that's red is not required. So far, it's all required. Okay, Roman numeral 3. It's very unusual to use Roman numeral 4 in related rates, but in optimization problems, you almost always have to use Roman numeral 4. Just like in related rates, Roman numeral 2 has your list of desirable variables. We want v and x. Everything else will be designated an undesirable variable. Here we go. Volume of a box. Volume of a box with a rectangular base is going to be LWH. And this Roman numeral 3 equation is going to be either one that's from some sort of list of equations, or you might have to create one on your own. But notice, have we reached our goal yet? Is it time to celebrate? No. This is going to take some work because all three of these variables are designated as what? Desirable or undesirable? Class? Yeah, they're all undesirable. Well, I know that length is always going to be 15 minus 2 times whatever x is. We saw that pattern in the warm-up thing. 11 minus 2x, 11 minus 2 times 1, 2 times 2, 2 times 4. In general, it's 2 times x. The width is also 15 minus 2x. What's the height of the open top box going to be? It'll just be x. Now, do we solve Roman numeral 4 equations for desirable or for undesirable variables? Friends? Can't hear you. So, okay, on 3, let them hear you out there on the World Wide Web. Undesirable or desirable? 3, 1, 2, 3.
Desirable.
Did you say desirable? No, it's always undesirable. You always solve Roman numeral 4 equations for the undesirable variable. That's the number one strategy for taking an antidote to MIGO. It's not an antidote. It's a vaccine. It's a vaccine. MIGO vaccine is to solve Roman numeral 4 equations for the undesirable variables, which they already are. So that means you know to not do anything else. Just substitute into the main equation, v equals 15 minus 2x, we got 2 of them, so it's 15 minus 2x squared times x. Woo-hoo. Or is it CP? The chest pounding is starting to die down. So, but there it is. That's the celebrated equation. And you're going to have to work hard to get the celebrated equation in optimization problems. That's really the main reason we celebrate. Usually it wasn't much work at all to get to the celebrated equation in related rates problems. It usually was the first one, but you're going to have to work hard to get to the celebration point. And the celebration is going to go on for a while. But ask yourself, is it dying down yet? Because when it does die down, it's time to move on. Now, Roman numeral 5, we always skipped it in related rates. And you can still skip Roman numeral 5. It's optional. But I'm going to show it to you anyway, because sometimes it's a good idea to do Roman numeral 5. In red, because it's not required. V as a function of x. Notice it's a polynomial function with zeros at 0 and at 15 halves, which is 7.5. What is the leading coefficient of this volume function? Is it a positive number or a negative number? Yeah, it's negative 2 squared, which is positive. So the leading term will be 4x cubed. If we were to take the time to expand it, you can anticipate that without actually doing the work. 4x cubed. So that means on the far right, we're going to, this, by the way, is an even x-intercept because of the 2 is an even number, that exponent. So it's going to come from the right, it's going to be positive, it's going to bounce and cross over. There's the volume function. Sure enough, as x gets bigger, the volume gets bigger and bigger and bigger, and so at some point it starts coming back down to 0. You can actually cut out too big of a square. If x is too big, if x is 7.5, you have no volume left whatsoever. Now, it would be a rookie mistake to think that, oh, I'll bet you the answer is the average of 0 and 7.5. No, it's not a parabola. This is a cubic polynomial. We're going to have to do the first derivative test. By the way, in an optimization problem, Roman numeral 6 is not the same as it is in related rates. In related rates, Roman numeral 6 is where you differentiate with respect to t. That's related rates. Roman numeral 6 is completely different. If you don't mind, yeah, Jack, if you would just put your phone into a bag, then it won't just be so distracting. So, friends, Roman numeral 6 is pre-calculus only. For optimization, that's where you take out your calculator. This is how you did these problems back in pre-calc advanced, except at this point, you took out your calculator and you did second calculate maximum, and you used your calculator to do what now we can do with the first derivative test. So instead of using the calculator, we're going to use calculus. So that's totally colored in red. We won't do Roman numeral 6 at all like that. Instead, we're just going to go to Roman numeral 7. And I'm going to put Roman numeral 7 down here so you can really see it. Roman numeral 7. 5 and 6, basically, most of you will be skipping them. Although if you want to just sketch the graph, it's worth it. Because now we know the answer to this problem will be somewhere between 0 and 7.5. Any questions? Do you have a question?
Yeah, what's negative r over there?
Negative r?
Yeah, Roman numeral 6.
Roman numeral 6. Oh, no, that's blank, comma, blank. Blank, comma, blank. Because you would find the coordinates of the relative maximum. It's just blank, comma, blank. You would go to your calculator and you would use second trace maximum. And you would find the maximum. So, but we aren't going to do that. We aren't going to use a calculator. We're going to not use a calculator. We're going to use calculus. So here's how we do it. Roman numeral 7 is the first derivative test. Or you could use the second derivative test. I don't care which one. But let's use the first derivative test in our first example. Okay, here we go. Let C represent a critical number of v of x. There's two ways to get critical numbers. One is to have v prime of C is undefined. And that happens when C is an element of empty set. There are none. There are no values of C that make v prime of C undefined. By the way, we haven't even found v prime. We shouldn't get too far ahead of ourselves. We should at least take the derivative of the celebrated equations. Let's do that. I'm getting this out of the way. So technically, yeah, it makes total sense to just, let's find v prime of x. Celebrated equation. Let's take the derivative using the product rule. Derivative of the first times the second plus first times the derivative of the second gives me derivative of blob squared. Seems like it would be 2 blob to the first times the derivative of the blob, which is -2 dx. We're differentiating with respect to whatever the independent variable is. So it's 2 times 15 minus 2x times -2. So that's derivative of the first times the second is x plus first, which is 15 minus 2x squared, times the derivative of the second, which is 1. So allow me to, in simplified form, write v prime of x as, this is -4x. Would you permit me to distribute a -4x to 15 minus 2x? That would give me -60 x, and -4x times -2x is plus 8x squared. And then over here we have, oh, actually, you know, I totally regret having done that because I missed out on an opportunity. I could have factored out a 15 minus 2x, so I apologize for that, but I really want to take advantage of that. The fact that both of these terms, both of them contain 15 minus 2x, we don't want to miss out on that. So when you factor out a 15 minus 2x, what's left in parentheses is -4x plus 15 minus 2x. That's a much better deal because I want factored form anyway. So that simplifies to 15 minus 2x times -6x plus 15. Nice. Okay, so that's the first derivative. Leave it in factored form. So critical numbers are where the first derivative is undefined or where the first derivative is equal to 0. And because it's in factored form, oh happy day, we see that the critical numbers are at the zeros at 15, 6, that's 2.5 and 7.5. So C equals 2.5, C is an element of the set, 2.5 and 7.5. Well, we knew 7.5 was going to be 1. If we did Roman numeral 5, we knew there was a horizontal tangent here, so it could be 2.5. So tell you what, just give me a second and just draw this 3-layer thing with the two critical numbers at 2.5 and 7.5, v prime of x and v of x. So since the leading coefficient of our derivative is
Tyler
positive,
Birchie, Thomas Nelson, please stop, and Abby Dagfall, please stop by the front office.
we would say v of x has a relative maximum at x equals 2.5 because v prime of x changes from positive to negative. That completes Roman numeral 7, based on which I can say the final answer is based on x equals 2.5. By the way, I have to use x equals 2.5 to fill in the length, the width, and the height, because the directions did ask for the dimensions, length, width, and height. But basically, as long as you know x equals 2.5, then you can use these 3 equations in Roman numeral 4 to calculate the length, the width, and the height. It comes out to be 10, 10, and 2.5 are the length, width, and height. Well, that's it. You've got 2 examples for homework. You are dismissed. Have a great weekend. Yeah, I'll spoil it.